All right, it's a pleasure to introduce Herbert Huppert, who's a retired professor of applied maths at the University of Cambridge. And he spent his career doing fluid dynamical modeling of all sorts of problems in earth sciences. So he'll talk to us today about some fluid flow problems related to coral reefs. He's got numerous awards, and he's also a fellow of the Royal Society in the UK. He's around for the next 2 days, and if anyone would like to have a chat with him, I'm sure he'd be very happy to talk with you. So with that, over to you, Herbert.
Well, thank you very much, Anya. It's very kind of you to invite me here and to introduce me. The only thing I'm upset about is her statement, retired. I wish that wasn't true. Unfortunately, she's correct. Well, thank you all for coming. It's very good. And those online, it's very enjoyable for me to be at Monash again. I spent a number of periods here and had a great time and even written a number of papers. And Anya, she didn't say it, but was a graduate student of mine in the time before I was retired. And a wonderful graduate student she was. Well, I'd like today to tell you something about surface waves over coral reefs and how to analyze them. And then most important, to use that idea to suggest how to defend against tsunamis. So for the first part, the waves over corals, I'd like to tell you something about the background, and then I'll tell you some fluid mechanics, and I'll tell you some field data to back up the calculations, some simple laboratory experiments, and then some conclusions. And then we'll go on to talk about what we can do with the results that we've obtained. Now, we're all used to waves on the ocean and the idea that they propagate. And the important idea quantitatively is that there's a dispersion relationship which links the frequency omega, which is 2 pi over the period, to the wave number, which is 2 pi over the wavelength, depending upon the depth of the fluid layer over which the waves are propagating. And of course, gravity is what plays the important role in their propagation. Now, there's a phase velocity. That's the velocity with which the waves move, the maximum or the minimum or some particular point that's given by omega over k. And that means it is the relationship which, you know, is this a pointer? No. Oh, you didn't know. That's okay. Oh,
this one is. I'm not actually sure how it works.
Oh. Well, let's go without that. Which is omega over k. It's just that this little arrow was so small, I can hardly see it. I don't know how you go. Which is this relationship, which is the square root of g over k. K is the wave number when the depth is very large. So that's the velocity with which the maximum moves or the minimum moves. And now there's another velocity, which is the velocity at which the energy propagates, and that's less than the velocity at which the wave itself propagates. So what that means is, for example, if you go to a pond and you throw a stone in, it'll generate a wave or a series of waves, and the first wave travels a little bit at the phase velocity, and then it gradually disappears. And what was the second wave becomes the first wave, and it travels a little bit, and then it disappears, and then so on and so on, because the energy goes at a smaller rate. And so the group goes not at omega over k, but d omega dk, which in this limit is half the phase velocity. There's yet another velocity named after Stokes, the Stokes drift. Stokes was a remarkable character Anya could have hardly said he was retired because he was allowed to keep this professorship, the one that Stephen Hawking then later had, for something like 54 years, and it was something like 90. I might just say when he was something like 92, but when he was 91, having spent his whole time in Cambridge since being an undergraduate, he wrote to a friend of his and said, you know, I've spent my whole time in Cambridge, but it's nowhere near as nice as it used to be. Over the last 50, well, it was more, 60 years, because he was an undergrad, it's grown to be so big. There's so many people around there, bicycles and cars. I'd like to get rid of them. And I desperately wanted to write back and say, come and see what it's like now. It's quite even worse. Anyhow, he introduced what's called the Stokes drift, which is second order in amplitude, a squared. So it's very much slower than either the phase velocity or the group velocity, and it decreases exponentially with depth, and it's purely horizontal. There's only a horizontal, slow second order in amplitude velocity. But it's really very important because that's what brings the driftwood and plastics and all that stuff to shore, is due to the Stokes drift. Now, I want to look at what happens if you have waves over the ocean, which is this clear part, and a coral reef, which I write down as this. And I'm going to make an approximation to get started that the coral reef is horizontal in its extent, in its uniformity, and this is a two-dimensional problem, and there's no doubt, and if some of you are graduate students, here's a wonderful problem to look at, problems that will say, what happens if the coral reef changes in depth? What happens if it's not two-dimensional? Lots of things still to be done. And that's another reason why I'm annoyed that I'm retired, that I can't have graduate students who would do all of this. Well, I want to use the standard fluid mechanics in the ocean part, Euler and Bernoulli. It's an inviscid fluid, and Bernoulli tells us that the constant pressure on this free surface, because the atmosphere is at a constant pressure, how to relate that. And then Darcy's flow, the equations for flow in a porous medium, and I'm going to model the coral layer to be uniform. It doesn't change its porosity or permeability or shape as the wave goes along, but there are definitely interesting things that can be done there. And then I have to solve it in here and link the two and see what happens to this wave. And you can already see from the diagram that the wave which is propagating to the right here is larger in amplitude than it is here. So the effect of this coral layer is to reduce the amplitude. And part of what we want to know is how much that is so. There's a lot of mathematics, and I'm not going to go through that. Really a lot of algebra. I'll just tell you what the result is after, as I've written down again, the ideas to get a dispersion relationship. And the dispersion relationship you get is here. Look at the top line in blue, and we'll just have a little check. If the permeability is zero, in other words, there's no real effect of the coral layer, then this left-hand side would be zero. That says that the right-hand side has to be zero for tan, something to be zero. That means the argument has to be zero, and we get omega squared of GK tangent KD, which is exactly what we had before, though I've used little d for the depth. But what we also see that there's an I here, square root of -1. So what we see immediately is that the solution of this dispersion relationship must have an imaginary and a real part to it. Well, all of these things are real, omega G, except for K. K, the wave number, 2 pi over the wavelength, is going to have to be imaginary. And since it's an e to the ikx minus omega t, that's how you describe a wave, that says there's going to be some change as the wave propagates. This is now the non-dimensional relationship, where J is in some sense an indication of what the porosity of the porous medium is. Delta is the ratio of the fluid depth to the total depth, and S is this other parameter that comes in, which this is going to be real, but we're going to find that the solutions here for R, the non-dimensional, oh, I don't have it here. R is non-dimensional by D. Oh, I do have it here. R is dk is going to be complex, i.e. there's going to be some change as the wave propagates. Now, if I take the left-hand side and put it on the right-hand side and just show you a contour plot for a case where the layer is taking out, the coral layer is taking up only half the space. You see there are zeros at these points here, but of course it's the whole variation with parameters that we want to look at. But for this particular case, the wave number is 0.76 plus or minus 0.28 I. Well, it can't grow with time. There'd be no energy to allow that. So it decreases with space, and that's what you see here. Now, to give you an example, here's a movie that shows the particle paths and how they go. Now, one of the things that you see immediately is that there is a vertical component, slow vertical component. Oh, I can't do that. Slow vertical component, that this is going upwards, saying that the effect of this coral layer is that the Stokes drift has some vertical part, and that implies there's an exchange of fluid between the coral layer and the ocean layer above it, clear ocean layer above it. And that's really very important because that means that you have food for the biology that lives in the coral layer brought down and junk brought up. And I'm terribly sorry, I've forgotten something that I meant to say right at the beginning, which is where I come from and where Anya did her PhD in the famous seminars on Fridays. The audience quite often interrupts and asks questions. Now, I'm used to that, and I think it's a good style because it may well be that you're going to ask a question and say, I don't quite understand what you mean by so-and-so, and nobody has understood it because I haven't explained it properly, or you're going to ask a question that is going to be interesting. So don't feel at all inhibited, interrupt and ask, and I apologize, I didn't say that before.
Excuse
here we go again. Well, just to show you what it looks like, and you see there's a vertical Stokes drift, i.e. vertical final component to this motion, which is circular.
Excuse
now,
me.
Here's an example.
Excuse me. May I ask you?
A delta. I don't know why it's changed its name.
Excuse me.
Where, as you see, there's only a quarter of a layer of clear ocean, and 3/4 of the layer is taken up with the coral motion. And you see there how the Stokes drift is bringing fluid down into the coral layer. Here's now different examples, and again, the D has gone to a delta. Oh, sorry, the delta has gone to a D, and this is what I've already shown you here. Now, if it's half depth, and you see this is really just a check when it's 0.99 of the fluid layer, the flow is horizontal. The Stokes drift is horizontal, just as he calculated. But it's an important vertical component otherwise. Here's now an example of how that Stokes drift changes, just for particular examples, amplitude and stuff, but just to give you some indication. As you go along, this is the horizontal component of the Stokes drift. Of course, rather small, but it gets less and less as we go in because the energy has been taken out of the flow. Well, this is now for a quarter coral layer. Here's for 3/4 coral layer. This is now the vertical drift velocity, and it's rather small, but it's still very important. Now, I became interested in the theory here because a woman called Mimi Curl, who's a wonderful biological oceanographer in Berkeley, came and gave a talk of the work that she and her group had done looking at the effect of waves over coral reef in Hawaii. And she showed this photograph of her measuring the velocity components and things like this. And she's a wonderful lecturer, and she quite frequently said, and the flow goes like this. And I said to, excuse me, maybe in Cambridge, you have to call that a Stokes drift. And she more or less said, who's Stokes? West Coast American. And I also said, has anybody looked at this theoretically? And she said, no. And I said, oh, wonderful. So I did some work on that. I might show you some of the results that she'd put dye into the coral reef, and because of the Stokes drift, the dye would come up. Was it not for that vertical component, it would have stayed in the coral reef. Now, I'd like to show you this photograph of a coral showing you that it's not an absolutely flat surface. I'm making an approximation here, but I don't think this humpiness makes any difference. A little bit down and it'll be exactly the same. But I'm sure sometime in the future, somebody, a good graduate student will write a paper of what's the effect of having a rough surface like that.
Can I ask a question quickly?
Please.
So the Darcy flow is like a sort of the approximation for that would be that it's laminar in there, low Reynolds numbers. Is that right?
It's a low Reynolds number laminar flow, and I'm assuming the most simple porosity and using Darcy's law. Now, it's always an interesting question in flow in porous media, in that you could have simple geometry, lots of balls one next to another, and a number of the laboratory experiments that I've done have that. On the other hand, coral no doubt grows upwards, and so there's not going to be, well, there is going to be an inhomogeneity, and there'll be a difference between vertical flow and horizontal flow, and that I've not taken into account. So I'm just presenting the simplest case.
Right.
May I ask a
Thanks.
question too?
Also, someone on the Zoom had a comment, which I would just relay because speaker is not working. Yuri Stefanyants said that he suggests that the Stokes drift phrase is incorrect and that it's a Lagrange drift as well. Maybe you can clarify if he that.
Oh, I'm giving the calculation for what the flow is at any particular point. Yeah, I mean, if I was to follow, I don't know how to tell him. Oh, he can see me. Oh. Yeah. Well, I'm sorry. I'm not giving him the variation. I'm telling him what the velocity is and what the velocity profile is at this point, and at this point, and then at this point. Yeah, but one could compare them. Now, this is some more experiments, field experiments of what Mimi did. You see one of her students dived underneath and put some dye into the coral layer, and slowly, not only does the dye come up because the vertical component of the Stokes drift because of the coral layer, but also it spreads horizontally. Well, that's the horizontal component. So a sort of a typical result is a horizontal component, order a centimetre of a second or so within the reef, and a horizontal velocity that increases with depth outside the reef, but an important typical vertical velocity of about 1.5 centimeters per second. And you see this sketch was actually made by Mimi. It comes to your question. It's not very homogeneous porosity because corals are lump. And I agree, I've made a simplification there. On the other hand, this is now some coral which Mimi took from Hawaii. And you see that's not badly homogeneous. It's not like spheres, but we could determine the porosity and the permeability in the lab from this. And the porosity you work out by measuring what the external volume is, and then you pour water into it, and you measure how much water you pour into it, and that goes into the clear bits, and from that you can work out what the porosity is. And the permeability we measured by putting it into a big flask and then putting a funnel on top here, and we could keep this funnel at a constant level of water that would flow through, but we poured water in, and so we know what the pressure is that's driving the flow. Whoops. So we know the pressure driving the flow. We know the rate at which it's flowing, and so from that we can work out or determine what the permeability of this is. Now, for different wave, excuse me, amplitudes, we can calculate the horizontal drift velocity, and Mimi's measurements are shown with these crosses. Excuse me, because it varied a little bit from one day to another and exactly where she was on the reef. And I thought it was fascinating that the first time we submitted this, the referee said, there's no correlation between the theory and the experiments. The authors don't seem to realize that the experiments had error bars associated with them, and the theory has no error bars associated with it at all. It's really quite wrong. Well, I have to laugh. Anyhow, the take-home messages are that Stokes drift in a high Reynolds number liquid layer above a low Reynolds number, as pointed out, porous lower layer, has a vertical component, and that's really important. This has important biological consequences because there's a way of interchanging fluid and the stuff in the fluid, the small biological stuff between the ocean layer and the porous coral layer. Now, there's no doubt some quantitative differences here, as I've already said. The coral layer may not have a flat top. It may vary. There may be three-dimensional variations, lots of possibilities. Okay, well, now I'd like to say something about tsunamis and how this suggests work on tsunamis. And I'll tell you a little bit about previous work on tsunamis. I'll tell you a little what I've been doing, some extra applications, and then some conclusions. And may I remind you please do interrupt at any time and ask questions or clarification. So, tsunamis are quite important, vigorous and energetic wave motions on the surface of water. They can be excited by earthquakes, by volcanic eruptions, by underwater explosions, by granular collapses in the ocean. There's a number of ways where tsunamis can be generated. They can have rather long wavelengths, hundreds of kilometers. It's possible, but I think I'm showing off a little bit. Many tens of kilometers, going up to 100. And great heights, again, tens of meters, I think is a little exaggerated, but it can be as much as that. But generally, it's only a few meters high. In some sense, the most famous tsunami was in Lefua Bay in Alaska in 1958. And there was a sudden and big granular collapse on the sea floor in Lefua Bay, and 50 million cubic meters of rock just slid, and that led to a tsunami, and nobody was killed there because it was in a part where there's no population. But going later, geologists could civil engineers could see that there was destruction some 525 meters up above the lake surface, so really quite considerable. Now, the Boxing Day tsunami, in which many of you will know, so you may have been little babies, but I remember it well, in 2004, killed 250,000 people, and there was $14 billion worth of damage. And it's worthwhile bearing that in mind, I think, because I'm going to suggest a way you might defend and save some of that money and some of the people. And there are things that you can say against my ideas, but when you say them, and please do say them, just remember I'm suggesting saving possibly the lives of 250,000 people and a few $1 billion of damage. So it's worthwhile paying, I'd say 2 and 6, showing my age, having been brought up in Australia, 2 shillings and 6 pence, as Anya said, a minute amount of money. And that's what we're going to talk about. The next slide I'll go through quickly. It's just a pretense of me enjoying a tsunami. I think that's a little exaggerated. There have been lots of geological investigations of the big tsunamis that have been generated, looking at what the effects would be in Santorini in Greece, in Heraklion. I might just say in Santorini, rather, it's interesting because while all of this happened quite some time ago, about 4 years ago, it was thought there might be another volcanic eruption. And Santorini is a big old volcano, and there was some chance. The magma around there looked rather unsettled, and the question would be, what would have we done had there been an eruption? There have been numerical evaluations of propagation speeds and sizes and what the effect of the ocean topography is on these waves. There have been some early warning stations put into the ocean, but mainly in the Pacific, not in the Indian. There was no early warning of the Boxing Day tsunami. And people have also built walls to protect the shorelines, but the problem with the wall is if it somehow disintegrates in part, that'll allow the energy to propagate through. And so a wall is only as useful as its very best bit. Just to give you an example of what destruction there can be, this is an eruption in 2011 that affected Japan, something like $200 billion worth of damage, and 20,000 people were killed. And you can see enormous amount of destruction in the housing. This is an effect of the Boxing Day tsunami due to the magnitude 9.1 earthquake. And part of the problem is that there's a ring of fire around the Pacific, and it's caused by the fact that there are plate motions that can go off at any time and form an earthquake, and that might well generate a tsunami and cause difficulties to a number of those places. Another situation which I think is interesting is Mount Pico, which you see here. And that's the highest point, the top of it, is the highest point in Portugal at 2 and a bit thousand meters, though it's actually on the mid-Atlantic ridge. It's not in mainland Portugal. And the question would be, if there was an eruption of this volcano and it put rocks and things into the ocean, you could have tsunamis travel all across the Atlantic here. You'd have trouble in this country here where I am a retired worker. And there are some areas along here in the United States that are really quite important. What would happen if there was an eruption here and a gigantic collapse? Well, would you end up with something like this? Real problem in New York. Think of the financial damage to New York and the number of people that might be killed. Last year, I was in Indonesia, and I couldn't help but take a photograph of this image. This is a tsunami hazard zone. In case of an earthquake, go to high ground or inland. Well, how are you going to do this? Are you going to ask if you can borrow a car and drive to inland, or is everybody going to be able to get away from it? Well, I don't think so. Well, I couldn't help smiling when I saw this a few weeks ago, a picture of a series of dominoes falling down, and what you want to do is to put something in the way to effectively stop the domino collapse. And that's what I'm really going to say, that I'm going to suggest how you could decrease the wave side, save lots of money and lives, taking away their energy, just like the man who's put his hand in the dominoes, by lining the ocean floor with a porous layer. So the idea would be that this porous layer on the ocean floor would absorb the energy of the overlying waves and reduce their amplitude. Well, of course, the idea is exactly the same as before. Here we use the equations that I've already told you. And let me show you a movie of a lab experiment showing you what will happen. But this lab experiment, for reasons I don't understand, doesn't always go as easily as I want it to. Come on. So here's a lab experiment. There's a tank, and this man, the technician, is exciting some waves, and you see the waves go, whoops, all the way to the end. Well, you've seen waves before. Now what should come on, I hope? Yeah. We'll put in a foam insert, so it's exactly the same as I've suggested. This film was made for me when I gave the talk a month or so ago, and it sometimes works and it sometimes doesn't work. I've never worked out yet. Some of you, here you go. Right, so he's doing the same thing, and we've put in a foam layer, and you see the amplitude of the waves is decreased enormously by this foam layer which takes out the energy. It acts as the porous layer. Well, the dispersion relationship is exactly the same as before. And what we can do is, given the parameters, the J and the S and the delta, the ratio of the porosity, to calculate where you'd want to be to get the largest value of the imaginary part of K. In other words, where the damping would be at its maximum. Well, to give you an indication, a rough idea for two different wave frequencies, 1 and 5 times 10 to the minus 2 per second, and two different depths, 100 meters and a kilometer. The optimum porosity, first in kappa in meters squared, and showing you something like 77% or 54%. So in the 54, it's half open space, it's half closed space. And what you'd need to reduce the energy by a factor of 2, so a half, is something like a kilometer, in the order of a kilometer. If you had 2 kilometers, you'd reduce it by 3/4. So when you think that the Pacific is thousands of kilometers across, to have this porous layer of 1 or 2 or so kilometers, a quarter of a kilometer, that wouldn't be too difficult. And you could also raise it off the bottom of the ocean a little bit. That wouldn't make much difference. And you might want to do that to allow the fish and everything to go on the ground. This just tells you the optimal conditions, are really just to show that we can calculate the optimal conditions, and having a very thin layer, as you see, not very good. You want, but you could get away with having a layer of something like a tenth, well, maybe a fifth of the ocean depth, if you want to have optimal conditions. This is now just saying again how it would change, but we can calculate the optimal conditions. So what I'd like to say is, I've told you that tsunamis can cause much havoc, causing hundreds of thousands of deaths and billions of dollars of destruction. And I'm suggesting this calculation indicates that you might well be able to lay down a porous mat and absorb the energy, and that would be worthwhile. People often ask me, and so did the referee, how much would that cost? Well, I don't know what the answer to that is, because I know how much it costs to buy a small amount of porous media or foam, but how much will it cost to build a kilometer worth, 2-3 kilometers worth, and maybe quite a few tens of kilometers in the other way, foam in the other direction? I don't know. You could imagine that there might be factories that built just for that. But I bet it doesn't cost hundreds of thousands, or as you've even seen, millions of dollars. So I think this could be a good way. And an example I often give is when the first motor car was designed, if somebody said, well, how much will that cost? Well, it would seem to be an enormous amount, I'm sure. I don't know what the actual value is. But now, of course, cars are made much cheaper. Okay, well, if I might thank Mimi Coyle, a wonderful biological oceanographer, and Joseph Weber, actually my summer student, who carried out some of these calculations for me. Well, I hope I've ended on time. And please do ask questions. Yeah.
So yeah, if you want to ask questions in the room, please can you use that so people online can hear you? Thank you.
Otherwise, I won't hear you.
That's right. Well, that was great. Thank you very much. Enjoyed that. So I can see why, obviously, it'd be a great thing to dampen tsunamis. but presumably you're dampening natural wave energy. So would that have deleterious consequences on other systems, biological systems, and so on?
That's a very good
Sediment
question.
transport systems.
Except, if you don't mind, I'm going to be annoyed you didn't ask it 10 minutes earlier and interrupted, because what I forgot to say is that there are areas, I can't speak with knowledge about Australia, but there are areas in Britain, East Anglia, the northern coast of East Anglia, where wave energy is taking away the shoreline and making cliffs just collapse, taking houses with them. Now, your point is, well, first my point, why I would like to have asked the question earlier, my mistake, is I think it could also be used there very effectively to stop coastal erosion. And my guess is that that happens here too. And now your question would be that stopping of the coastal erosion would also dampen the waves. And if you're a surfer, you wouldn't like that, because you want to have nice big waves. Yeah, there are disadvantages and advantages to everything. I mean, coming back to cars, we all find them wonderful and they take us from A to B, but we all at times say, damn those cars, why are there so many cars? I wish there weren't cars, which in some sense cars hadn't been invented. So what you say is true. That it will have consequences for the wave motion, just the wind-generated waves. How bad is that? And are you willing to take that, not to have 250,000 deaths and billions of dollars of damage?
There's a question here from online, which I'm going to read out for you. From Aman, Gebra, Michael, Kid and Miriam, which is that coral reefs are not only porous, but also rough. I'm curious to know your take on how the roughness, especially in the shallow wave case, is going to influence the mass transport under the waves. I'm referring to the Longueuil-Higgins drift near the bottom, which at times could be more dominant than the Stokes drift.
And then he's saying the bottom topography is no doubt...
They're saying that the surface of the corals is rough and could be approximated with a roughness length scale, and that the influence of the roughness on the Stokes drift in the shallow wave layer is greater than the influence of the Darcy flow within the permeable layer. Or if that's a case, if that's a case you've considered.
Right.
I don't think that would be so. And what I would say is that, first of all, tsunamis propagate over the ocean where there is this surface or roughness, and they're hardly diminished at all. The roughness there doesn't play a role. I think that would be very much second order, because the wave really is propagating, and there's a good approximation to an inviscid flow. Longueuil-Higgins, who I knew, and with him I never got on with, is up there, is possibly up there. He would no doubt disagree. But I don't think surface roughness will play much of a role.
Okay. I have a question. So the experiments that you did and the setup of the theoretical problem that you're looking at sort of considers the porosity within the coral itself, right? And that's pretty sort of nice problem to study. The thing I can't wrap my head around, though, is the separation of scales between that, which is, you know, a coral a coral body that's got a porous media that's maybe this size, and an extremely shallow ocean potentially, which is maybe only a few tens of centimeters tall, and the actual problem, the applied problem that you're suggesting that this applies to, which is a coral system, which is full of, you know, water without coral in it, and waves or oceans that are meters deep, right? Tens meters of deep. In the flow that's within the coral layer, the majority of the flow is not going through as Darcy flow through the corals, right? It's going around the momentum, the inertia in the system. The high Reynolds number flow in the bulk of the coral layer is like between the corals. So how do you, what thing about that system allows you to make the approximations for Darcy flow in the coral layer, or be confident that that's a good approximation?
Well, can I put your question in a slightly different way, but it is still your question. How good in real large-scale situations are fluid mechanical theoretical ideas that have been around for 100 years or so and have worked fairly well? Well, I agree that I'm making quite an extrapolation. And I also agree that the next step would be to get a big wave channel and try it out and compare the theory with the experiments. In fact, last year when I was in China, somebody showed me a wave tank that was 1/4 of a mile long and said, "Would you like to do some experiments here?" And I said, "Oh, yeah, that would be fabulous." Whether something will come of that, I don't know, but I hope so. But flow in porous media have been used on pretty large scales quite effectively. I think you might say that using it on the foam layer that I have in mind is more reasonable than on the coral layer, because without a doubt the corals grow upwards, and so it's not a homogeneous isotropic media. But I think it would work. Well, it's the idea that I'm trying to put over, and I agree that's the first approximation.
So what about sand instead? What about flow through sand instead of corals?
Well,
that's a far better idealized system.
Well, sand is pretty impermeable. I mean, luckily, the sand on the bottom of the ocean, and the water doesn't really percolate through. The porosity is really so close or so small that you don't get much effect due to that. Now, I mean, as you saw, the values of the porosity and permeability that we think would be best, you don't have to do it best, is it a sort of larger value and quite reasonable? I agree with you. I'm taking an extension and expanded view. But, you know, you could say the Navier-Stokes equations, we tried them out and they should work on a small scale, but they seem to work on the meteorological scale quite well. Weather forecasters are now doing better and better.
But those are well beyond the, you know, those high Reynolds number flows that got that nice scale-free property. There's a question. Well, I guess one comment I have is that, you know, in systems that do have this, that there's a lot of boundary layer meteorology studies of flow through tree canopies, right, which is quite a similar problem. And there, what they do to get their vertical momentum fluxes and trace glass fluxes and their effective roughnesses and their permeabilities, residence times, all these things, is that they set some sort of dampening scale. They just have an effective viscosity profile, and they don't make a Darcy flow approximation within the canopy layer, because because of the problem, but because of the thing I just described, which is the majority of the flow is going through as turbulent. That work has had a lot of field verification with eddy covariance towers and things like that. It's quite nice work.
That is important, and this is really mainly the work, at least as far as I know, of Heidi Neff and her group at MIT. But the important things, and I've discussed this with Heidi, is that the trees in the boundary layer of the Earth move back and forth. And that plays an important role in her.
Heidi's experiments are in quite strong inertial flows, like in flumes. But the work I'm talking about is someone like Ili Bouzid or Marcelo Chimecki at UCLA or Princeton, and they have these studies where like the flex of a tree in the Amazon is very low relative to the flow momentum. There's a question on here from Richard Manasseh, which is if there's a vertical flow in the porous reef, by continuity,
I didn't hear the first part.
If there's a vertical flow in the porous reef, by continuity, there should be a return flow. Is there some horizontal scale over which that vertical flow reverses?
Yeah, that's the wavelength will tell you. Yes, he's quite right. And that's the important thing, that there's a vertical flow both into the boundaries and out of it, which is quite right.